I want to turn to a particular solution, which is a complete solution, but for a limited case. And the limited case is knowing the reflectors, knowing which buildings the signals are reflecting from. And we need to know this because we have underlying all of this work is a chicken and egg problem. Let me explain the chicken egg problem first. The non-line of sight errors or the reflected errors are a function of your position. That's the one. If there's anything you take away from this talk, you should take that away. If you think about it, when you're standing in a street and you're measuring a reflection, if you move, the reflection changes. If you move away from the building, the reflection from that building gets longer. Conversely, if you move closer. So if you knew your position exactly, then you could work out those reflected errors and you could remove them and you could compute your position. So there's the chicken egg problem. We don't know our position. But that very problem, if you express it in math form, gives you a solution. If you say, well, these non-line of sight errors are a function of my unknown position, x, y, z, and I write an equation for that, well, then I've got an equation in x, y, z, and I could solve for x, y, z. And I'll take you through how we do that. I will do a 1D case, then 2D, then 3D, and then show you the solution. And then finally, I'll show you an equivalent solution which involves reflecting satellite positions around the plane and creating something called virtual satellites. And I'm going to show you that because it's kind of interesting and it involves a really important subtlety that might not occur to you right off when I first show it to you. And this is the first chance for some audience interaction, so stay alert. Okay, so let's go look at the 1D case. So imagine in 1D, there's a satellite out there to the right. You're standing there. The unknown in this case is delta x. That's the thing we're trying to figure out. Where are you in this 1D space? The known values are x sat, the position of the satellite. We'd get that from the ephemeris or from the assistance of assisted GPS. And the range or pseudo-range measurement, which here is line of sight, so we've labeled it PLOS. So just imagine this very simple example, and you asked to solve that. Well, clearly the answer is delta x is x sat minus PLOS. So if you follow that, congratulations, you are now a navigation engineer. Let's bring in a building. So now let's just suppose as a thought experiment that that building manages to block the line of sight, and by some magic, the non-line of sight signal sneaks by the building and bounces off the building behind you and arrives back. Now, clearly this cannot happen in one dimension, but there's just a way to think about it to get us going, and this will get more realistic as we proceed. So now, the unknowns are still delta x, but PLOS is now unknown because you can't measure it because it's blocked. And the knowns are still the position of the satellite and PNLOS, PN loss, the non-line of sight measurement. So now what we do is we just write the unknown, P loss, as a function of the known measurement and the thing we're trying to solve for. And you can clearly see this is the relationship that the P line of sight is P non-line of sight minus 2 delta x, because the non-line of sight has to go past you and come back. So now we have our unknown value written in terms of something we know and the thing we're trying to find, plug that into the original equation, solve for delta x, and you're done. And just try and remember this, there's a minus 2 delta x in here. You'll see that again later as we get more realistic. Okay, so in 1D, you can solve this problem. In the 2D case, now the two dimensions here are x and z. Now the satellites have some elevation. The elevation of the satellites is known and essentially the same for the line of sight ray and the non-line of sight because the satellites are so far away that these rays are practically parallel. How close? They're within 0.0003% of being parallel, so we can assume they're parallel and it doesn't change our result by more than a fraction of a millimeter. And so we know this elevation. And by some geometry shown on the top right here, which I won't go through, but I think it's quite easy to see and believe that multiplied by cosine of elevation puts this, gives you a projection onto the horizontal, and you get back to the 1D case, which we just solved. So you have this delta P, which is the difference between the non-line of sight and line of sight, as defined there, is just the 2 delta x with now the cosine elevation term. And of course, if elevation went to 0, we revert back to what we had the previous slide. So now I hope you get the gist of where this is going. And with 3D, you have a slightly more complicated picture. Now the rays are coming out from behind your screen towards you. If we set up the coordinate system so that x and z are the same and y is in line with the building, then the azimuth with respect to the building is that angle there. And so now I think you can see that multiplying by sine of azimuth is a projection onto your screen. You're back to a 2D solution, which from then with the cosine L takes you back to 1D, and we're back to a solved problem. And again, you can see here, if you set L to 0 and as to 90, you'd get delta P equals 2 delta X, the original 1D. So you see how we build this up. And then if we go to the 4D algebraic solution and work through the math, which I'm not going to do, the classic nav equation, which many of you will be familiar with, you've got your pseudo-range residuals here. You've got this line of sight vector, which is represented here. So this is the first term, second term, third term. And you've got your common bias, delta T here, and a 1 there, and a matrix like this. This matrix equation, which is true for line of sight signals, just with this modification, which I derived from the stuff I've just been through, gives you a closed form solution for non-line of sight signals. And now, even if all the signals were non-line of sight, if you filled in these rows appropriately for each satellite, you could solve this problem. So I thought that's nice to show you because it's a technical meeting. There needs to be at least some math in it, I think. And here's an alternative and equivalent approach to show it, which in a way is even more elegant than what I just showed you. If you take that same situation and take the real satellite and then construct a virtual satellite by reflecting this ray about the plane that it's bouncing off. So now we get this virtual line of sight. If you do that for each of the satellites and then treat the virtual satellite as if it were a line of sight satellite, it then solves the problem in the classic way, that just using classic GPS techniques. Okay, however, there's an important subtlety. Do you notice these asterisks here? The subtlety is that the normal GPS solution, you have to take into account the amount of time it took for the signal to leave the satellite at transmit time and travel all the way to Earth and get to you at receive time, which is some significant time later, about 70 milliseconds. And in classic GPS, you have to rotate the reference frame of the Earth to account for that passage of time. And so you have to work out your position at the time of reception. And if you don't do this, by the way, the Earth will have rotated by 20 to 30 meters, depending on where you're standing, in that amount of time, and you'll get the wrong answer. So when you come to reflect the plane, so this is the audience participation part. Here's a little quiz for you. When you're reflecting this satellite around this reference plane, what reference plane are we talking about? Is it the reference plane at the time of transmission? Is it B at the time of reception? Is it the average, or does it make no difference? So I encourage you now, if you think you know the answer, use the chat in Zoom. Put in the chat if you're feeling bold, send it to everybody. You can prove that you knew this all along and get some brownie points. And I'll give you a chance to do that, or share with your friends, or just write it down on a piece of paper, or just remember what you thought. And the answer is B. You must use the reflecting plane location at the time of reception. I'll briefly walk you through why, because it's an interesting thing to look at this subtlety of GNSS, and it's like many things in GNSS, something that's perfectly obvious when you first look at it, and the more you think about it, the less obvious it gets. And that's what makes our subject so interesting. So the satellite sends the signal at time of transmission. So clearly that's what we care for about the satellite, is where the signal came from at the time of transmission. And then the signal travels to the Earth. During that time, the Earth's rotating. So when the signal arrives at the building is at the point where it's going to be at the time of reception. So the only thing that matters is where is the building at the time of reception. Where the building was at the time of transmission is of no relevance to anything. And so that's the answer. Where is the building at time of transmission? At time of reception. It's where is the satellite at time of transmission? Where is the building at time of reception? Now, if you got that right, pat yourself on the back. Remind your friends. And if you notice that there's actually another subtlety on the subtlety, which is that strictly speaking, it's really where is the building at the time the signal hits the building, not the time of reception, which is where the signal gets to you. However, that slight difference of the time of hitting the building to you is typically around 2 microseconds. in typical city geometry, and the Earth rotates less than 1/10 of a millimeter in that amount of time. So we can safely use time of reception for our calculations without making any difference to the noticed results. So in summary, for this limited case, either using the substitution of the known measurements for the unknown measurements and making them a function of the unknown delta x, or using a reflected satellite position, and in either case correctly accounting for the Earth's rotation, we can solve this problem, which at first glance seemed insoluble. So that's great. However, so are we done and can you go home? No, we're only halfway through, because unfortunately, there are several things that break the assumptions that we just used in that exercise. Number one, there are many different reflectors for each signal. If you're used to seeing a diagram that shows you a single reflection, such as I drew by hand in the previous slide, those diagrams are very misleading. This picture here is not a hand-drawn diagram. This is actually from Google servers where we do this for real. These are all the rays from a single satellite. These rays going out to space are not going to many different satellites. They're all converging on a single satellite. This is how many rays you get converging on a typical location in a fairly benign city environment. This is the medium rise part of San Francisco. When you go into the high rise, it gets worse, as I'll show you later. So you get many different reflectors from each signal. Also, the reflectors are not mirrors, but they are scatterers. And you can kind of see this here, that there are many different paths that converge on the same path. This could not happen from the mirror, but buildings are not typically mirrors. They scatter the signal, and so you get even more rays than just the rays you would get from many different buildings. Now, each of these two is not fatal to the math we just did. You could expand that math, and it's actually an interesting area of research, if any of you are looking for something like that, to add in all these different terms to what I just showed you. However, the third thing really does kill the previous approach, which is often, actually usually, we don't even know what street we are on in the first place. And this example that I showed you before, this was the background to an earlier slide. The red here is the ground truth, and the green is from a smartphone. This is very typical. This is a high-rise part of San Francisco. So here, for example, we're almost in the wrong city block, and particularly we'd think we were on this street if this was the position, the raw position from your GNSS receiver. So if we were to use the technique I just described, we'd be using these reflectors, which are the wrong reflectors. The signal is not reflecting off these north-south facets of the building. It's reflecting here. And so we need something more general than known reflectors. And so that leads us into the more general solution, which we've implemented at Google and which I will walk you through now.